Hello everybody and welcome back to the chapter 4 of this ROS Navigation course. We are very close to the end, guys. We are almost done. We are in the last chapters, these path plannings, which has part 1 and part 2, which we will do in the next chapter, in chapter 5, but we are almost there. So in previous unit, we have already covered and seen how to do mapping in navigation, how to create a map of the environment, and also how to do localization. So how to localize our robot into that map that we have created. So now the last part is to actually make the robot navigate, autonomously navigate. So make it move from a point A to a point B without colliding with any obstacle. Yeah, that's basically path planning. Then, as always, let's start with using Rviz, how Rviz can help us in doing path planning. And basically, for visualizing path planning, we will need three elements. A map displays for visualizing the Costmaps. You are going to see later what are these Costmaps. We will need path displays for visualizing the plans, the trajectories that the path planning calculates. And finally, we will be using as well the 2D tools. Okay, so let's go with this first example here. Then, first of all, let's launch this command that will actually start the path planning system, the world navigation system, in fact. So let's execute this command here. Let's also start an Rviz. There we are. Then we are going to open the graphical interface window. And there we have Rviz. Okay, we already have it with robot laser scan and the map. Let's configure properly the laser, because this is not the topic for this simulation. In this case, the topic is scan. There we have our laser beams. And then, okay, we already have a map. Let's duplicate this, because we are going to use to. Here, basically, I'm going to be following this example. So, okay, so we have two map elements, and then let me add at least one path element. There we are. And I'm going to also add a pose array element in order to visualize localization. Okay, here we have it, the pose array. Excellent. So now we need to properly configure these elements. So first of all, this one, we are going to set it to this here. Let's make this a little bit bigger. Okay. So as you can see here, we have the global Costmap. There we have it. Here we have our global Costmap, okay? Which is, it's similar to the regular map, but it's a little bit different, as you can see. You will see later why this difference. And then for the local Costmap, we are going to select here the local Costmap. There we are. And let me switch this in order to differentiate them better. I'm going to put this to a Costmap color scheme. There we are. Excellent. And finally, let me configure this path to this one, to the nav FN ROS plan. Okay? Which basically is the global planner. You will also see later in this unit what this is, okay? So don't worry if now you are a little bit lost. This is just an example exercise to see a little bit everything together and to start getting in touch with this path planning system. So let's select this topic, Excellent. For now, nothing appears yet. This will be displayed when a path is calculated, okay? Then the first thing we need to do will be to localize our robot. So as you can see, our real robot in the simulation is not here. It's not in the center of the room. It is here, more or less at the side of this bench, and it's facing that way. So I'd say that more or less I can place it. I'm going to use the 2D pose estimate. You already know this tool, yeah? I'm going to use this 2D pose estimate tool, and I'm going to place it around here. I think more or less it's here. So let's put it there. There we are. Okay, the pose array is not yet configured, so let me put here also the topic, which is particle cloud topic. You should know this from the previous chapter from localization. And then, okay, yeah, I have more or less the robot localized. As you can see, the laser beams are matching the actual map. Here I have the global Costmap, which is this, which is like a regular map, but with the walls and the obstacle a little bit wider than the regular map. This is because of inflation. You will see later what this is, don't worry. And here we have the local Costmap, okay, in colors. So now, what I'm going to do, I'm going to use this 2D nav goal tool in order to send a goal to my Husky robot. I'm going to say, hey, I want you to come here, okay? Then, as you can see, a green line appears, which is the path that has been calculated by the path planning system to go there. And the robot actually, as you can see, it's moving there. Okay, there you are. Oh, it is going there. And now here, when it reaches the goal, it says goal reached, okay? And I can say, okay, great, now I want you to come, I don't know, here. So a new plan is calculated, it is displayed here using this path element, and the robot starts going to the new goal position. As you can see, okay, there it is. Here this local Costmap keeps updating and changing. There we are. And now it will say goal reached when it has arrived. Now it is trying to put the correct orientation of the robot. So the point is reached, but it's trying to match the orientation, the correct orientation. There it is, goal reached. Now it's perfectly set. Okay? So yeah, basically you have seen in this example the whole path planning system working. In fact, the whole navigation system working, because we are using the map we created in the mapping chapter. We have also used localization at the beginning, as you have seen, and finally we have also used the path planning system. So in fact, in this example, we're using the whole navigation system, okay? And as you can see, basically the elements we need in order to work with path planning are this path element in order to visualize the plans that are being calculated. The global plan, in this case, it's this one, but there is another, which is the local plan, okay? Which we are going to see in the next chapter, in chapter 5, okay? In this one, we are going to focus only in the global plan, the global planner. And also the map displays, in order to be able to visualize both the local Costmap, which is this one I have here in colors, and the global Costmap, which is this one in black and gray, okay? So basically these are the main elements for working with path planning in Rviz. You can also, of course, use the pose array for localization, laser scan to visualize the readings of the laser, whatever. But the main ones are this map and the path elements, and of course these 2D tools, which are the 2D pose estimate to localize the robot, because obviously if the robot is not properly localized in the map, you won't be able to perform path planning. Yeah, so you need to, before doing path planning, you need to have your robot localized in the map. So that's why we first used this 2D pose estimate, and then we have this 2D nav goal tool, which basically allows us to set goals to our robot, to say to our robot, hey, I want you to go here. You set the point and the orientation you want it to go, and then the path planning system will automatically calculate the best trajectory in order to reach that goal position. Okay, so basically, yeah, this is the wall example we have been seeing. So yeah, okay, let's do one thing before closing this. I'm going to save my configuration so that I have it for later use, for using it during later in this unit. So let's save this config. Let me save it, in fact, as nav.rviz. Yeah, going to save it. Yeah, replace it. Okay, excellent. So yeah, well, I'm going to close this for the moment. Excellent. So let's begin with the proper explanation. So yeah, the move base package. Okay, what is the move base package? Basically, the move base package, what contains is the move base node, which is probably the most important node in the whole navigation stack. Okay? Because the main function, the function of this move base node, is to move the robot from its current position to a goal position. Yeah? So when using Rviz, I set it with the 2D nav goal tool, I set it a goal position to my robot. The ROS node that is in charge of providing a trajectory to reach that goal position is the move base node. Yes? And basically, this move base node is an implementation of a simple action server. Yes? So of an action server. And this action server takes a goal pose. Yeah? So therefore, since this is an action server, you can send position goals to this node by using a simple action client, of course. And these goal positions are provided through the move base goal topic. Okay? So, for instance, if I now do a... Okay, now I don't have the move base node launched, but if I launch the move base node, which I have it here in the command I executed for the previous example, with this command I'm basically starting all the navigation system with the localization and the move base node, basically these two nodes. So I'm launching the IMCL node, which is the node for localization, and the move base node, which is the node for path planning. Yeah. So now, if I do here ROS topic list, let's do this bigger, I can see here this move base goal topic, yeah? And through this goal topic is where the move base node receives the goals. Okay? I have it here. So, let's do one thing. Let's launch again Rviz. There we are. Okay, there we are. So now what I'm going to do is to basically repeat the process I did before. But I'm going to do a ROS topic echo at the move base goal topic. Okay? So now I don't get anything, nothing is being published. Yeah? But now I'm going to send a goal to my robot. So, okay, I'm going to use this 2D nav goal tool. I'm going to say to my robot, hey, come here. Okay, so what happens now? As you can see, a new message has been published into this move base goal topic. Yeah? So basically, by using this 2D nav goal tool in Rviz, what I'm doing is to publish a message into this move base goal topic. Yeah, that's basically what is happening there. So I'm publishing a message into this move base goal topic, and this goal, the goal I publish into this topic, is received by the simple action server that is implemented into the move base node. Okay? So this is basically what is going on here, what is happening behind the scenes, let's say. Yeah. So I publish a message into this move base goal, and then this goal is received by the move base node, and then it calculates the proper trajectory. Okay, we are going to go a little bit deeper on this later. Yeah, but yeah, basically this is it. Okay, so okay, yeah, here we have a small exercise, which is to, instead of sending the goal through the 2D nav goal tool, send it through publishing directly into this move base goal topic. So it would be something like publishing directly through the shell, ROS topic, pub to move base goal topic, and you would need to guess which kind of message this topic uses. For instance, ROS topic info move base goal. This way we can get the type of message that this topic uses, which is move base messages, move base action goal. Whoop. So now you can simply do a ROS topic pub to the move base goal topic, then place here the message, move base action goal, and with a double tap it will autocomplete the message, and this way you can fill this message, and this way basically you are going to be doing the same that you do when you use this 2D nav goal tool, which is obviously it's visual and it's much more nice to use, but you can also publish directly to the topic, of course, and this exercise asks you to basically do that. Yeah, then okay, let's move on. Okay, yeah, of course, here I don't want to skip this part. So here basically it's telling you that because this move base node basically it's an action server, besides the move base goal topic we have already been seeing now, you have obviously all the topics that an action server has, which are the cancel topic, the feedback topic, the status topic, and the result topic. Yeah. So, for instance, if here I do a ROS topic echo of the move base feedback topic, I will be able to visualize the feedback while the action is taking place. So let's publish a new goal. Let's move it here. There we are. And as you can see, I can visualize the feedback of this action server. Yeah. I could also visualize the result, the status, whatever I want. Yeah. It works just like a regular action server. Okay. Great. Yeah. So this exercise here, basically, it's to visualize all these topics that are taking place. Yeah. Here, sending the goal. Here we have the feedback topic. the status topic, the result topic, okay, to visualize all these topics that take place into an action server. Great, then let's continue here. Okay, yeah, you have another exercise here. I'm going to be skipping some exercises because if not, this video will take forever and I don't want to give you all the solutions. So yeah, this exercise 4.4 basically what does is to send a goal in a different way. So until now we have seen how to send a goal using this 2D nav goal tool. You have also seen through an exercise how you can send a goal by directly publishing into a topic. Here it is. By using the ROS topic pub command. Well, by using the ROS topic pub command into the move base goal, yeah, you saw another way you can send a goal to the move base action server. And then here you have still another way in which you can send a goal, which is by creating a action client. Yeah. So basically here what you should do in this exercise is to create an action client that sends a goal to the move base action server. Okay. And in fact, this action client will send 3 different goals. Yes, so it will first send a goal so that the robot goes there, then it will send another different goal, for instance here, and then it will send yet another goal, for instance here. So this send goal client py script you will create will basically be sending these 3 goals continuously. Yeah, so the result will be that the robot moves infinitely to the 3 goal poses provided. Yeah, so this is basically exercise 4.4. Excellent, so yeah, we have seen basically how this move-based goal topic works, how you can send goals to the move-based node. And yeah, summarizing, basically what happens is when this move-based node receives a goal pose, it links its goals to other components such as the global planner, the local planner, the recovery behaviors, and the Costmaps, and generates an output which is a velocity command. Yeah? And then it sends this output, this velocity commands, to the command bell topic so that the robot can start moving towards reaching that goal pose. Yeah? So this is basically the process. The node receives this goal pose you sent him, and then it does some kind of calculations here using the global planner, the local planner, the Costmaps, etc. And it returns you, it outputs velocity commands which are sent to the command vel topic. Okay? And that's why the robot starts moving in order to reach that goal. So, okay, here we have another exercise, exercise 4.5, which basically we are going to start touching some parameters. Of course, this move-based node has parameters, as you have seen in the SLAM mapping node and also the AMCL node. You had lots of parameters to configure, and the move-based node is exactly the same. For instance, in this exercise here, we are going to modify this controller frequency parameter, which basically controls the frequency in which these velocity commands are sent. Yeah. Then, before being able to do this, we need to create the structure. Yeah, because until now we have been working with this launch file. With the launch file, we use it in the in the example, let's stop this for now. Okay, there we are. So we have been working with this move base demo launch file, which is inside the Husky navigation package, but this is a package from the system. This is a demo which is already configured. So we will need to create something in our workspace so that we can modify and tune and work with all these parameters and launch files and modify them without any problem. So in order to create this structure, I'm going to do this with you. You need to follow these first steps here. So basically, first of all, we are going to create a new package named my move base launcher. So let's go to our workspace and let's create this my move base launcher package. There we have it. Then here it is. Yeah. My move base launcher. Then inside this my move base launcher, we are going to create two new directories, the launch and the params directory. So launch and params. There we have them. And then inside the launch directory, let's go inside the launch directory. I'm going to create two new files, this move base launch 1. Okay, in fact, let me create them here. So I'm going to new file, there we are, which is going to be called my move base launch 1 dot launch. Let me copy this dot launch, and another one which is called my move base launch 2. There we are. And inside the parameters directory, I'm going to create a new file which is called my move base params.yalm. So let's create this file here. There we are. So we have our structure here, our my move base launcher package, with a launch directory that contains these two launch files and a params directory that contains these parameter files. All of this is empty right now. So now it says have a look at the move base demo launch and move base launch files of the Husky navigation package. Also have a look at the planner.yaml file of the same package. So as I've said before, here we have been working until now with this move base demo launch file. Yeah. So let's have a look at this launch file, which is inside the Husky navigation package, as you can see here. So let's go to the Husky navigation package. There we are. And here I can see this move base demo launch file. So let's have a look at this move base demo launch file. Okay, this has opened wrong. There we are. Okay, so as you can see, basically what this launch file is doing is, first of all, it loads a map. Yeah, so it loads the map of the environment with these two lines here, with using the map server node. You have learned this in the previous chapter. And then it basically launches here the AMCL node with this launch file, and here it will start the move base node with this other launch file. Okay, so basically it loads the map and it launches the localization system, the AMCL node, and the path planning system, the move base node. Okay, so let's come now to this move base launch file. And as you can see, here is where actually the move base node is being started. Yeah, as you can see, here you have the move base node which is being started, and here you have a lot of parameter files that are being loaded. Okay, you are going to see all these parameters during all this chapter and the next one. Okay, But basically inside this file is where all the parameters are being loaded. Okay? Great, so we have checked the move base demo and the move base launch file, and then we also have this planner.yam file, which is also in this package, but it's in the config folder. Here you have it, the planner.yam. Yeah. Here we have this. Here, basically, we have some basic parameters of the planners. Here we have parameters for the navfm global planner, trajectory planner. Also here the WA planner, which are planners. And here we have also this controller frequency parameter, which is the one we are going to modify for this exercise. So, great, we have these three files, and now we need to copy the contents of all these files to the files we have created in our package, so that we will be able to modify them and tune them. Okay, so basically, let's do this. So, Husky navigation. Okay, so let's copy the contents of the move base demo. Have this figure. Okay, the contents of the move base demo launch file to our home user Catkin workspace src, my move base launcher launch, my move base launch one.launch. So we copy the contents of this move base demo launch file to the move base launch one file. Okay, and then we copy the contents of the move base launch file to the other launch file we have created, which was my move base launch 2. There we are. So now, inside our launch files, we have here the contents. We have here the contents of the move base demo launch file, and in this one, we have the contents of the move base launch file. Okay, great. So now let's copy the last file, which is the parameters file. Sorry. So let's come here to the config, and we are going to copy the planner YAML file to home user Catkin workspace src, my move base params, my move base params.yam. So we are going to copy also this file, and now if we open this one, we will have the parameters of the planner YAML file. Excellent. So now, okay, yeah. Okay, excellent. So now, modify the my move base launch one launch file so that it loads your second launch file, and modify the my move base launch 2 launch file so that it loads your move base parameters files. Obviously, yeah. So now we have copied exactly the same contents of the other files, but now we need to do some modifications so that we actually use these files. First of all, in the first launch file, okay, the map can be left like this, also the AMCL, because we are not working on this in this chapter. But here, we want to launch our launch file, yeah? So basically here what we are going to do is to modify this. We are going to put here the name of our package, which is my move base launcher, yes? And here we are going to put the name of our launch file number 2, which is this one, yeah? So my move base launch 2. Okay, So now this launch file will start this launch file, not the one we have installed, okay? And then inside this launch file number 2, instead of loading the planner YAML file, we want to load our parameters YAML file. Yes, right? So we are going to do the same. We are going to modify here the name of the package for our package, which is my move base launcher. Here we have it. The name of the folder it's not config is params. So let's modify this. And finally, the name of the YAML file is not planner is my move base params.yaml. Excellent. So we have all our environment properly set up with this launch file starting this one, and this launch file loading this parameters file. So now you can perfectly come to the parameters file, modify whatever value you want. For the case of the exercise, is this controller frequency parameter. And if you launch this move base, this launch file, the number 1, you will start the whole navigation system, but using your parameter files. Okay, so this is why we have done all this setup now. I wanted to do it with you so that you have this clear, because it may be a little bit confusing. Okay, so now you already know how to set up the system in order to be able to modify your parameters and whatever. You are going to be doing this also in future exercises, so the process will be exactly the same. Yeah, in this case you have already launches, and you will probably have to add some more parameter files and maybe modify something in this second launch file. But the first one will stay like this for the rest of the course. Yeah, you won't need to modify nothing else here. Excellent. So yeah, you can finish this exercise, modify these parameters, see how it affects, etc. But now let's continue with the explanation. So the next thing is to talk about the global planner. So basically, when a new goal is sent to the move base node, when it receives a goal, this goal position is sent to the global planner. Yeah? And then the global planner is in charge of calculating a safe path in order to arrive to that goal pose. Okay? So the global planner is the one that calculates that path that we were visualizing, if you remember, with a green line. Yeah? So when the move base node receives a goal, it sends this to the global planner, and the global planner calculates a safe path in order to arrive to that goal pose. Okay? And this path is calculated before the robot starts moving. So this path will not take into account the readings that the robot sensors are doing. Okay, this is very important. So the plan that the global planner calculates, it's calculated using the static map. Yes? So it uses the map as it is when you created it. Yeah? So it takes into account the obstacles that are placed into the map. If, for instance, a person enters the cafeteria and starts moving, this won't be detected by the global planner in a first instance, okay? Because that person is not in the map, in the static map, okay? So this is important. The global planner calculates its path using the static map, okay? So it doesn't take into account the readings of the robot sensors. Yes? Excellent. So here you have an exercise in order to visualize the global plan. You remember here, let's do this bigger. Yeah. Here you have this green line. You already visualized it in the example, so let's skip this exercise. And also to visualize the global plan topic, because obviously this information is published into a topic. So yeah, here you have exercise 4.6 to do it yourselves. Yeah. Then when you set the goal, as you have seen, the robot automatically starts going to that goal. Yeah. So when you set the goal, the robot will automatically go to that goal position. Yeah. Then sometimes you may want to just calculate the path, but you don't want the robot to execute that path. For instance, it could happen. Then for that, there is a service called make plan, which just calculates the path, but the robot doesn't execute, doesn't go. Yeah, doesn't execute this path, doesn't go to the goal position. Yeah, you can do that with the service make plan. Okay, here you have an exercise also to test this make plan service. I will leave you do it by yourselves. Then, okay, we have different kind of global planners depending on how they calculate the plans. Yeah, for instance, the NAFFEN, which is the most commonly used, the most popular. Yes, this NAFFEN. Here you have a representation of how this planner calculates the best trajectory to reach the goal. You will see now. It does like mappings with points, and then it gets the best trajectory depending on the cost each point has. Well, this is more mathematical things. But yeah, basically you need to know that you have different planners, different global planners. Each one calculates its plan in a different way, and depending on your needs, depending on your situation, you would prefer to use one or another. Yeah, basically the most used is this NAFFEN planner, as I've said. Okay. Then yeah, here you have an exercise in order to see how you can change this planner. Usually it's drawn like this by setting the base global planner parameter. Yeah, and here you have for instance, to set the NAFFEN, the carrot planner, the global planner. Yeah, usually this is done in a parameter file like this. So you would add this line. You would add a line like this into the parameters file, usually, for instance, here. Yeah, you would do something like this. But in this system, the base global planner is, well, you can do it like this if you want. You can put it here. But in this system, the global planner is set here directly in the launch file, as you can see. The base global planner parameter is set directly here. It takes this base global planner argument, which is set here. Base global planner NAFFEN, as you can see. Yeah. So in this exercise, you have to modify this global planner. Yeah. Use another one. I don't know. For instance, in this case, it's the carrot planner, I think. Let me see. Yeah, here I have it. I didn't show it. So in this exercise, you need to change the global planner you set and use the carrot planner. So, for instance, you can, if you want, let me take it here. You can, if you want, come here and modify it directly here. Yeah. So put here in the global planner, change this for the carrot planner. You can do this if you want, or you can, if you want, comment all these this global planner line, this one here and here, and add it to the parameter files as you prefer. You can do it as you want. Yeah. But the thing is that you need to change the planner. So for instance, if I do it here, yeah, when I start my move base launcher, when I start my navigation system, I can check into using the ROS parameter server. Yeah, ROS param get move base global planner. This way I can get which planner is being used, is loaded. Yeah, and as you can see now, I have loaded the carrot planner. Yeah, and basically, let's put back the nav fn. There we are. So basically, in this exercise, what you need to do is to test. It's a quick exercise to test this carrot planner. By sending a goal which is into an obstacle. Okay, you will see why. Basically, it's because the navFAN planner doesn't allow you to set a goal which is into an obstacle. Like for instance here, this is an obstacle. This is detected in the map as an obstacle, and with the navFAN planner you cannot set a goal here because it says, hey, this is an obstacle, I cannot go there, and you will get an error using the navFAN ROS planner. But using the carrot planner, you can set goals which are inside an obstacle. And then what this planner does is to create like a straight line, and it moves the robot to the closest position from that line, and before it hits the obstacle. Yeah. By the way, you will see that with this exercise. You can do it by yourselves. And then, yeah. So let's keep going. Yeah, here you have some navFAN parameters that you can tune. Yeah, so here into the parameters file, you have here the navFAN ROS parameters. In this case, you have only two set. These are unknown and default tolerance. Here you have the explanation of these parameters as some other. Allow unknown. We have the planner window X, planner window Y, cost factor, neutral cost, and lethal cost, which calculate the cost of the paths. Yeah, well, here you have also a small exercise to test a little bit these parameters. So yeah, summarizing, in order to summarize this, I think this video is getting too long. So summarizing this, you have, when you send a goal to the move base node, this goal is sent to a global planner. Then this global planner calculates the best trajectory in order to reach that goal. Then you have different kinds of global planners. Each global planner calculates the best plan in a different way. So depending on your needs, you can select one or another. Yeah. And of course, you can customize, you can set parameters to these plans and make them work as you want. Okay? And then, very, very important, this, as I've said, this global planner calculates the trajectory based on a static map, but it is not a regular map like the one you saw in the mapping chapter. This map is the Costmap. Yeah? And what is a Costmap? A Costmap basically is a map that represents places that are safe for the robot to be in a grid of cells. Yeah? So it creates cells, it divides the map in cells, and each cell has a binary value. Okay? For instance, these values can be 255 for no information, so reserved for cells where not enough information is known, so for unknown space, 254, which indicates that a collision causing object was sensed in this cell, okay? You have 253, which is inscribed inflated obstacle, so indicates that there's no obstacle in this cell, but moving the center of the robot to that cell will cause a collision. Yeah? So because of the dimensions of the robot, despite in that cell there is no obstacle, if you move the robot there, the borders of the robot will collide with something. Yeah? That's basically this. And then the zero value for free space. Yeah, so basically it divides the map in cells, and each cell has a value of these ones. Yes? Then basically there exist two types of cost maps: the global cost map and the local Costmaps. And the main difference between them is the way they are built. The global Costmap is created from an static map. So this global Costmap is created from the map you built in the mapping unit, in the mapping chapter. Yeah? This global Costmap is created from that map. And the local Costmap is created from the robot sensor readings. This is the main difference between them. Yes? Then the global planner uses the global Costmap in order to calculate the path to follow. Yes? Then this is the global Costmap. Yeah, it looks like this. You saw it in the first example, if you remember. You had a map which was representing all the environment, and another one which was smaller, which was in color, which was the local map. Okay, the global Costmap basically what does is it takes the map that you have created, and it inflates it. Yes? It takes the map and it adds this inflation, which are these colors you can see here in the obstacles. Yes? Because, why is this done? Because depending on the size of the robot, on the dimensions of the robot, on the footprint of the robot, you will have to inflate more or less the obstacles. Yes, this is called inflation. Yes, you will see a little bit more on this in the next chapter also. Okay? So you can see here, yeah, the global Costmap is created from a user-generated static map, as the one we created in the mapping chapter, yeah. Okay. And the global Costmap also has its own parameters, which are defined in a YAML file. Here is an example of a parameters file of a global Costmap, yeah? We have a frame, a static map to true, rolling window to false. You can see here what this means, and some plugins. Okay? Then basically, Costmaps are defined in 3 different parameter files. One for the global Costmap, another one for the local Costmap, and another one which is for both Costmaps, which defines some things for both Costmaps, which is called the common Costmap parameters file. Okay, so parameters for Costmaps are basically defined in 3 YAML files. For instance, let's come a second here to the Husky navigation package. And as you can see here, you have the Costmap common, the Costmap global static, and the Costmap local. Okay, basically these 3 are the ones that are being used in this system. Okay, these are for other setups, but the ones that are being used by this system are the Costmap local, the Costmap global static, and the Costmap common. So as I've said, you basically have 3 parameter files where you define the Costmap parameters. And the Costmap parameters basically are these ones. You have the global frame, which by default is map. You have the static map parameter, which is a boolean, true or false, which defines whether or not to use a static map to initialize the Costmap. Usually, for a global Costmap, this will be true. And then the rolling window, which basically it's just a boolean, and which basically says if you want to build the map from the sensor readings. Okay. Then in a global Costmap, this static map will be true, and this rolling window will be to false. Because as I've said, the global Costmap is built from a static map. Okay? Then in the local Costmap, when we see it in the next unit, this will be the contrary. So the rolling window will be true and the static map will be false. Okay? But for the global Costmap, the static map has to be true and the rolling window has to be false. Okay? And then finally, you have these plugins. Okay, which we are going to have a quick look here. And basically this is a sequence of plugins specifications, one per layer. Each specification is a dictionary with a type and 9 fields. Okay, basically this plugin says what layers you want to load into your Costmap. Okay, you will see what layers are in the next chapter also. Okay, but basically for global Costmaps you will have 3 layers. You will always load 3 layers, which are the static map layer, the obstacles layer, and the inflation layer. Okay, basically these are the 3 layers you will use in global Costmaps. Okay, and then finally, yeah, you have here a small exercise in order to, yeah, so copy the contents of the Costmap global static YAML file to the Husky. Yeah, so here basically you have to create a new parameter files for the global Costmap in order to be able to tune some of these parameters. So here you would create a new file, my global Costmap params.yaml file. You will paste the contents of this Costmap global static to home user Kotlin workspace src. There we are. And here now you have the parameters for the global Costmap. And now here in this exercise it will ask you to modify some of them and see how they affect to the global Costmap. Okay? And yeah, I think I will leave it here. We have reached the end of this chapter. So yeah, good luck with all the exercises in this chapter, and see you in the next one, where we are going to talk about the local plans and the local Costmaps and some more things. So goodbye.